Okay, so another example, let's see, for class 18, and we're going to take a look at an example that's actually in Sengel right here, okay? So this has this commercial airplane. It's got a total mass of 70,000 kilograms and a wing planform area of 150 square meters. And the plane has a cruising speed of 558 kilometers per hour and at an altitude of 12,000 meters, where the air density is given to us as 0.312 kilograms per cubic meter. The plane has double slotted flaps like these right here for use during takeoff and landing, but it cruises with all the flaps retracted. Assuming that the lift and the drag characteristics of the wings can be approximated by this wing profile that we're seeing right here, determine the minimum safe speed for takeoff and landing with and without extending the flaps, the angle of attack at cruising steadily, to cruise steadily at the cruising altitude, and the power that's needed to be supplied to provide enough thrust to overcome wing drag. Okay, so we have a lot of things going on here. Let's see. Some of the first things I'm going to do is I'm going to write down some data. So at ground, the density is going to be equal. We're going to use 1.2 kilograms per cubic meter of air. So that's the air density, mass density. And then at 12,000 meters, we're going to use a density of 0.312 kilograms per cubic meter. Other things I want. Well, let me go ahead and turn in our velocity at cruising speed is 558 kilometers per hour. Let's just turn him into meters per second. So that's really, we usually just divide by 3.6, so we get 155 meters per second. I wonder if that was the actual number that we came up with, or they're rounding off 5.6. Yes, okay, cool. So that's the cruising. How does it go? Cruise. I don't know. Cruise with an E on it. Cruising speed. And anything else I want to get? Let me get the weight. Right. So the weight is going to be the mass times gravity. So we're going to say that our 70,000 kilograms times the 9.81, and that ends up coming out to think 686,700 newtons. All right, and we're off. Okay, so we're going to use our main equation here for lift. It's going to be the lift coefficient times 1/2 rho v squared a. And so if you want to find this minimum velocity, what we need to say is, well, what's going to determine the minimum velocity? And that's really all about the stall, right? So they show the stall, they even put the number in there, that this is the coefficient, lift coefficient, the maximum lift coefficient. And we want to do it with and without the flaps. So we're going to use a 3.48 here and a 1.52. Now, something you don't necessarily know because you didn't read the book, well, you could read the book, is that so let's write it somewhere. FAA requires V min to be equal to at least 1.2 times the stall velocity. So what we're going to find the stall. We're going to find what this of stall velocity is going to be at these two conditions without the flaps and hair, and then we're going to multiply it by 1.2 to answer this question right here: the minimum safe speed to take off and land without extending the flaps. So we want to avoid the stall condition there. So we can solve for v squared, not v squared, we'll solve for v by taking the square root of the 2 times the lift and divide it by rho, I'm losing it. Okay, the lift coefficient and the area. So for no flaps, we have V, let's call it stall, and I'll call that 1. And we'll take 2 times this lift, which has to equal to the weight, so 686,700. Divide by, this is on the ground when we're taking off, so we're going to use the ground 1.2. And this one's no flap, so that's a lift coefficient of 1.52. And then the area we were told up above was 150. So with that, we get a speed of 70.85. These are meters per second. So with flaps, we'll have V stall 2 equal to the square root of 2 times 686,700 divided by 1.2. And now we have the difference here is going to be that we're going to use the larger 3.48 for the flaps. 3.48 for these flaps, and then 150 for the area, and we end up with 46.82 meters per second. So to answer their question, the Vmin, let's go without flaps. Vmin 1 is going to be 1.2 times 70.85 meters per second. And that's going to end up being 85.02 meters per second, which we can multiply by 3.6, right? Because that's going to be 3,600 seconds per hour. But we need to divide by 1,000 to get from meters into kilometers. We end up getting 306 kilometers per hour, or kilometers per hour. And then with the flaps, the Vmin 2, 1.2 times R 46.82, and that's going to end up getting 56.19 meters per second, which we find out is 202. So the flaps really make it so that we can go at a much, it's going to take us a lot less to lift off, and we can slow down to a much slower speed right there. And that's going to help us with the braking, right, on the runway. So it's a really useful thing for us. So, okay, so that's part A of this. Now we want to go for part B. And we have this question here, like, okay, so the angle of attack to cruise steadily. So what we want to do is we want to figure out, if we're going to steady cruise, what is the required lift. And they said that this plane doesn't use any of the flaps when it's in cruising. It says that somewhere. But it cruises with all flaps retracted. So we want to use this right here. So what we want to find is what the lift coefficient is, and then we'll be able to figure out, spoiler alert, it's going to be near 10 for the drag coefficient. So we're going to rewrite the equation for this as lift divided by 1/2 rho v squared a right here. So that's, again, the lift has to be equal to 686,700, and we are at the cruising speed, so we need to make sure we're using the density, which they gave us as 0.312 at that higher altitude. They gave us the speed of 558, so we found out that was 155. squared, and then we had 150 square meters. So we end up with a lift coefficient of 1.22. Now we could go to this little graph, but I have done some little kind of funny thing here. Is I put this graph inside of Excel and did a bunch of monkey business. I don't know how useful this is, but I did it anyway. And I came up with equations for each of these curves. I even came up with equations backwards for these curves over here on the right-hand side. And this is where I've reversed the x and the y, so now I have equations in here. And I plotted them up here at the top. So like, and I even have it so you can see where I move in here. So like if I were to go for 12 right there, and see that spot shows you where the lift coefficient is, and then it also you can use that lift coefficient over here to figure out what the corresponding drag coefficient is. But I found equations for them so that I can just get that answer right there. So if I want to try to find, this is the one with no flaps, that lift coefficient, I can use something called goal seek, and it's underneath data and the what if, and I can actually click on a cell. It says what cell. I want to set that cell equal to 1.222 by changing this angle. And if I do that, it just monkeys around with it until it figures out what that value is, and it tells me that that angle of attack is actually let's call it 10.8, because it's not like really exact and precise. But you can kind of see this is about where it's going to be, that 1.22, like right in that region. And it's off of this curve. There's some amount of error in here because I don't have it perfectly lined up. But I think the error is going to be less than if you just by your eyesight and putting it into the thing. So anyway, that's what I did right here. And I estimated that my angle of attack is approximately 10.8 degrees. And while we're doing that, we could use that lift coefficient back over here. We could use the lift coefficient that we find, that 1.22, and work backwards and find what the drag coefficient is. And it gets to be really close, and you can see over here, to 0.03. Like there's hardly any difference right there. So 0.03 is what we'll say that the corresponding drag coefficient that we will get for this angle of attack. And so this was part B right here that we answered. And I think up here, let's see, this is part A that we answered. So down here, we're going to do part C. And we want to find first what's the drag. And that's going to be that drag coefficient times 1/2 rho V squared A. So 0.03 times 1/2, and this is the flying density, so up in the high altitude, and we have 155 squared, and then 150 for our area, and we get 16,867 newtons. And so if we want to get the power, we remember that we take the drag and multiply it by the speed, so we get 16,867 times our 155, and we're left with 2.614 E6. These are Newton meters per second, because that's a Newton meters per second. But we could divide that by 1,000, and what we will find for our power is we have 2,614 kilowatts. And so that is answer C. And I'm right there at the 14-minute point. So that's a good example right there. Once again, that's out of Sengel, so give him credit. That's good problem. Thank you.